Greetings and welcome to yet another edition of QuantSlob. This is 9 in our foundational series, and this time we're on part 3 in our 3-part terminology and symbols micro-series. To close out this micro-series, we're going to run it straight up the middle, so to say, and offer some basic conventions and examples of symbols commonly used in math and stats. As much as the field of stats relies on math, which is quite a bit, there are certain general conventions or standards or norms, but like with all conventions, they are commonly stretched. Starting off, the most popular placeholder for some value or attribute or unknown of interest is typically lowercase x. But other letters are commonly used like Y, Z, W, U, V. Those representing the tradition of mathematical analysis like to reserve the letters F, G, and H to refer to some function of our creation. One essential construct in probability theory and stats, to be sure, is the random variable. And we will be visiting random variables soon upcoming in this foundational series and beyond, to be sure. The choice of letters is just about the same as earlier, those used to placehold unknown quantities, X, Y, Z. However, there's a tradition of using uppercase, italics, or leaning letters, and I'm not sure if there's a definitive opinion on the origin of this tradition. There may be a connection going all the way back 300 or so years to Thomas Bayes, who used uppercase italics M to refer to an event. And since some value of a random variable can be considered an event, this is not an unreasonable connection. If you're not comfortable with vectors or matrices or arrays for that matter, suffice for now that they represent special types of collections of individual values. The letters used to placehold a matrix or a vector can be quite varied. Usually matrices are symbolically represented as uppercase bold and vectors as lowercase bold. This, by the way, is my own preferred notation and that of a lot of others. Sometimes if somebody's writing on a piece of paper or on the board, they'll underline the letter to indicate a vector. So let's nestle a little closer to our area of focus. X bar here, not to be confused with something called X bar theory in linguistics, is very commonly used to represent the sample average of an attribute quantity X. The Greek letter mu is commonly used to represent the population average. Notice that we have a little X subscript here on the mu, which I think is always a good idea so that we know we're denoting the population average of the attribute X, as well as representing the average of an attribute's values within a population or sample. We're also going to be interested in representing how variable or varied an attribute's values are within a population or sample. The standard deviation is a common measure of this. For population, we use lowercase sigma. For the sample standard deviation, we kind of had two choices. S is more generic, I think, but we can also put a little hat, see a little hat over there, over sigma. But this usually implies that the value is to be used as an estimator for the population value. But honestly, I don't know if anybody's ever lost sleep over the distinction. If an attribute is a factor, meaning it is categorical, we will want to be able to speak in terms of proportions. And because a factor may have many categories, we can use the subscript to be more explicit about just what proportion we're talking about. Index notation, great convenience. Don't confuse index notation with math indices, which is something very different. We may have some collection of values of an attribute and want to be able to refer to each value. This works not only if the indices are explicit, like if we have a list, but also implicitly, like if we don't necessarily know or care about the order of the values. We can use subscripts. Commonly for convenience, as we have here, these subscripts will simply be counting numbers like 1, 2, 3, and so on. So just to give an example of how this can be used, for example, suppose we have a collection of numeric quantities and we want to take the grand sum, that is sum over all the values. And just to note that addition is commutative, just like multiplication. The order of the values in X, how they're indexed by the counter I, is unimportant. A constant, not surprisingly, is a quantity that is unchanging. A very common constant is the number 1, and we can use the Arabic numeric numeral symbol to represent the quantity 1. Given some particular context or setting, some particular mathematical problem, constants can be symbolically represented through many characters. However, the symbols that we looked at earlier to express unknowns or arbitrary quantities are usually not used to indicate or refer to constants. There are a number of constants, as we know, used throughout science and mathematics that don't have an exact decimal representation, and two I'm guessing you're going to be familiar with are pi, the lower Greek letter pi, and e. Both of these happen to be so-called transcendental numbers. Pi is the ratio of a circle's circumference divided by its diameter. E is the base of the natural logarithm. And while these symbols usually are reserved to represent these quantities, there are exceptions, and the context will provide the exceptions that provide clarity. So every time you see the lowercase pi or a lowercase e, don't always assume they're referring to these quantities. For example, pi has become popular in Bayesian stats to refer to a prior distribution, and e, of course, is famously used to express some quantity in units energy. And that's it. That's going to do it. That caps off our microseries on terminology and symbols. Thank you very much for tuning in, and don't forget to stay tuned for more QuantSlob.